So this is the second lecture on physical layer. The first lecture was how to send a bit. The second lecture is how the bits get there. So we were too much concentrated mostly on the sender side. Now we are going to concentrate on the medium side. And the medium here is the wireless. So we will talk about terms such as reflection, diffraction, scattering, fading, shadowing, multipath, Fresnel zones, and so on and so forth. Now here's the thing, most of this, if you were to take a course on wireless communication, they will spend a whole semester on these things. But we are networking course, not the communication course, and therefore we want to spend most of the semester on the rest of the layers. So we are still trying to cover up so that we know these things, because if you don't know these things, then you won't be able to design the right protocols. So the radio channel has these issues. First of all, the loss depends upon the distance and frequency. So what frequency you choose? Somebody had asked the question, what is the effect of frequency on things? And there is a big effect. So we'll talk about that. And of course the distance. And not only the distance, everything that is in between along the path. Noise, what else is happening around you? Shadowing. So shadowing, we'll define that shadowing too, whatever is in between. Frequency, dispersion, motion basically, Doppler spread, interference. Another name for noise, but the interference is more basically between people. So noise could be, like in this room when I'm talking, the noise could be coming from these appliances and light and electricity, but the interference would be if you start talking, then two signals, they will also interfere, right? Multipath, and we saw in the previous slides, a previous module about something coming back from the mountains. So you have the signals is coming not from from one place, it is coming through the wall, coming reflected through the ceiling, and so on. So you get multiple paths, echoes. And inter-symbol interference, ISI. Basically, when I send you 5 bits, and the next 5 bits, they might collide. They might become bigger actually, as we'll see, that the 5 bits, they start this small here, by the time they reach to you, they are this big. And the other 5 bits also, they started just next to each other, but by the time they cut to you, they are bigger and they interfere with each other. So even if nobody else is speaking, my signal will interfere with itself. Okay, so all of these I haven't defined yet. And so I will define, first of all, antenna. So the antenna, previously we used to be able to see the antenna on everything. So there was an antenna on the car, there was antenna on the computer, and there used to be. Nowadays antennas are almost all hidden. And so there are antennas on my computer, but you cannot see them. And only if I put a big router here, wireless router, then there are some antennas you can see. And so what the antenna does is, it converts from electrical to electromagnetic waves. Electrical itself is electromagnetic, but whatever comes through the wire, it just gets out into the air, and that's what antenna's job is. And the receiver does the opposite. So on the transmitter side, the antenna sends it out into the air. On the receiver side, it receives it and converts into electrical energy so you can process it. And the same antenna is used for transmission and reception. So if you have one antenna, the same thing is doing both jobs. The receiving and transmitting, you don't need two. And generally they are omnidirectional, and that means that they are sending power in all 360 degrees in all directions. And well, actually 360 degrees doesn't really tell you, but it's not only horizontal, vertical, whole sphere, the energy is going up and down everywhere. That is omnidirectional. Directional antenna will transmit most of the energy in one direction. So here is the directional antenna, and you can design it so that most of the energy will go in this direction. Whereas you can design it so that the direction energy goes into all the direction. Or if you were to measure the energy, you will find that it is almost in all directions same thing. Okay, so this is omnidirectional and this is directional. And directional antenna, basically most power goes in the desired direction, because if I am talking to you, I really don't want the energy to go up or sideways or backwards. That will be waste of the energy. So sometimes we use directional antenna. Isotropic means omnidirectional. Basically, isotropic means equal in all directions. And then if it is, and then basically, depending upon how you design the antenna, you might get more power than the isotropic antenna. Okay? So if you design the antenna, then as you can see here, the power here is much more than what an isotropic antenna will give you, and so the ratio of the two is called the gain, antenna gain. So when you buy an antenna, if you go on Amazon and you buy an antenna, it will say 3 dB antenna, 7 dB antenna, 5 dB, 9 dB antenna. Basically what that means is it will give you 9 dB more power than an isotropic antenna. Okay, so the power received is equal to power transmitted times the gain of the transmitting antenna times the gain of the receiving antenna times lambda upon 4 pi d whole squared. Lambda is the wavelength and d is the distance. So if you have a sphere of radius d, if you have a sphere of radius d, it has an area of 4 pi d square. Right? The sphere, right? And so, okay. So basically, this is the formula by which you can calculate the PR. So all you need is the transmitting antenna and the receiving antenna. Either one could have a high gain. So if the transmitting antenna has a high gain, you get more power. If the receiving antenna has a high gain, you can receive more power. Alright? And all these powers are not in dBs though, right? This is a multiplication. So here's the kind of confusion. When you have to put the power here, you really have to take a log if you want to do it in dB, and then that will say that dB power transmitted in dB plus the antenna gain, which could be 3 dB, 5 dB, whatever, plus the antenna gain, plus, so on and so forth. So everything will become plus. Right now it is all multiplicative. Yeah.
So is this gain mean for like an antenna with like a 9 dB gain? Is that inherently not omnidirectional?
Well, what it could do is, right. It doesn't have to be omnidirectional. Basically, it could not transmit in the vertical direction and put in horizontally equal all the dimension, all the direction. Okay. So it could be 360 degrees, but not vertical.
Okay. Because if it's in all directions equally, it's isotropic.
Yeah, right. Then it's isotropic.
So are those power ratings for a specific direction of the antenna?
Or basically this is between the receiver and the transmitter, right? PR and PT. So every place it will be different. If I measure it here, it will be different than over there, Right? And if there are 15 computers here, it will be different. Ellie, what are you doing on the computer? Huh?
Notes.
Okay, all right. Make sure that it is notes only. Any other question? No question. Then we move on to other effects. So basically, when somebody transmits a signal, it goes in many ways. First of all, it can get reflected. Right? If there is a building or a wall, signal will get reflected and there will be a phase shift. Okay? If there is a lamp post which is very thin, it can get scattered. Okay? And if there is an edge, it can get diffracted. Not that it makes any difference to us in our analysis, but we need to know these terms: reflection, scattering, diffraction. Here it got reflected, then got reflected here again. And so if you are here, you will get signals from several places by reflection, by diffraction, by scattering. All right? And all of them will have different phases, different magnitude, and yeah.
Is scattering to go other directions or
Yeah, right. So there's no one ray to one ray here. Scattering could be, scattering, the word says that it is scattered all over, right? If I throw something at you, it is scattered, right? As opposed to reflection, etc. is more directional, right? Scattering, of course, goes, okay. For reflection, etc., you can actually calculate the angles. If you did physics in high school, you probably learned about how the light reflected and how you calculate the angle and so on and so forth. So those formulas still apply. We won't do any of that. I just want you to know the three terms. That's all. There are different terms that people use. Scattering is generally when you meet a very thin object, and then diffraction happens when there is an edge, and reflection happens when there is a solid thing somewhere. Okay? All right. So reflection surface is large related to the wavelength. So when we say thin or thick, it has related to the wavelength. So the related to the wavelength of the signal, it is reflected and may have a phase shift, may cancel out original or increase it. So because of the phase shift, it could just cancel out the original signal. So you may get a 0 because the signal reflected in that one, right? I could increase it. Diffraction, if the edge is large related to lambda, and may receive signal even if no line of sight. So even if you're not in the line of sight, you can get the signal. So suppose you are here and the car is here, you can't see it, but you get it by diffraction. And scattering, when the obstacle size is order of the wavelength, lamppost, etc. If LOS, line of sight, diffracted and scattered signals are not significant, reflected signals may be. So let's go back. So if you are right here, let's say you are right here, line of sight. Okay, then these things would be small compared to what you get directly. Okay, and if no line of sight, diffraction and scattering are the primary means of reception. Everything makes sense so far? Okay. So now the electrical engineers worry about these things, and what they do is they develop models as to how much signal will be received if I transmit from the antenna, and so that is called a channel model. And this is called a channel. This medium between the receiver and the transmitter is a channel. And received signal can be, now the thing is there are mathematical methods which require convolution, and you can do that. Basically convolution in time is multiplication in frequency. So this is the thing, and I don't need you to go to in this too much detail, but if you start doing research in wireless, or if you start working with people in wireless, like I have worked with people who are pure physics people or pure electrical engineer, then when they talk you have to understand. Right? So basically then we need to know what this convolution is and all that. So basically anything, when you do convolution in time domain, it becomes a multiplication in the frequency domain and the opposite. So frequency and the time domain are always opposite. Okay? And we had talked about that the signal looks like an impulse in the frequency domain, but it is a sine wave in the time domain and so on, right? So those things basically, they just come naturally after you have done it a few times. So the signal X, after propagation to the channel H, becomes Y, where Y as a function of frequency. So you can plot it as a function of frequency. What is the power? YF. Y as a function of F is H as a function of F times X as a function of F plus N as a function of F. So everything is a function of F, but H is the channel model, X is the transmitted signal. So this is sent and this is received. So they basically multiply. Okay? So somebody can give you an HF, a formula for HF, and then if what you are transmitting, you know that, you multiply those two, you get the received signal, except that there is some noise on the way. N is the noise, which is added. So HF is the channel response, NF is the noise. Note that X, Y, H, N, all frequency, signal frequency, are all function of signal frequency. For example, the noise here is not equally distributed at all frequency. In some frequencies, only bigger noise. Okay. So this noise clearly is a function of frequency, and the signal that I am sending is also a function of frequency. For example, I am speaking right now. It's not really a radio wave, but sound wave also same thing applies. Basically at some frequency there is a lot more power than other frequency. If a female starts speaking, the frequency shifts, as we talked about before, right? The frequency at which power is more is different, and so on. So every speaker actually has a different frequency. So is this channel model clear? All right. So path loss. So power is distributed equally into a spherical area of 4 pi d square. Okay. So basically when you send it, it goes in all the directions that we saw before. So the received power is proportional to the receiving area. So receiver is not going to collect the power from the whole sphere. It is going to have an antenna which could be, sometimes you have seen these parabolic antennas. If you drive by near NASA buildings, I don't know how many of you have, but basically not NASA building, even not NASA building. If you just drive by some big hotels, on the top they have these big antennas, right? Why they are big? Because they want to collect a lot of power. If they have a small antenna, then they will not get that much power, particularly if it is coming from the satellite. So basically, the farther the object is and you want to receive them, then you want to have a bigger antenna. So this is AR is the area of the receiver, PT is the transmitted power, GT is the transmitter gain, and 1 upon 4 pi d square is the area of the sphere. 4 pi d square is the area of the sphere, right? And so if you have an area AR, this is how much you will get. And now if you call the gain of the antenna as 4 pi upon lambda square AR, and this is what sometimes gets confusing, right? If you put GR equal to this, then you get this formula, and that's why I have to think for a minute as to why 4 pi is inside this square. Because this is how the GR is defined. The gain of the antenna is defined 4 pi times lambda square, so 4 pi gets twice. D is already squared and lambda is already squared. Okay, so this was the previous formula we had seen before. PAR is equal to PT GT GR lambda upon 4 pi d square, and the reason it is like this is because the antenna gain then doesn't depend upon the lambda. In this case actually it always depends upon the lambda, but basically so that this formula comes out. This is known as Fresnel law, whatever, I don't know how they pronounce this name, but Fresnel law. And as you can see with this, lambda means wavelength, frequency on the bottom. Lambda is C upon F, right? C upon F is lambda. Speed of light divided by frequency is the wavelength. Right? If any of you have done the homework on number 3, which most of you haven't, if you had done, then you would remember that formula right away. C is equal to lambda upon F. Sorry, lambda is equal to C upon F. And C is equal to lambda times F. So anyway, so F would come out in the bottom. That means that the gain, the power will reduce as the frequency increases. That means the loss will increase as this frequency increases. So there are many things that I can ask. Power is the received power. When it decreases, the loss increases, right? Attenuation is loss. With the frequency. So that's why high frequencies are not very good, right there. And that's why most of the world started with low frequencies. So we started with what we would call frequencies, and then we went to HF, high frequencies, and then when they got filled up, then we went to very high frequency, then we went to ultra high frequency, UHF, VHF, UHF, and then we said no, high doesn't make, so we went on, and then now we are using, I don't know, there are no names for it, but basically now we measure it by gigahertz, and terahertz and so on and so forth. Okay? Alright, so this is one thing we learned. But from this formula it is clear that the attenuation increases with frequency. Is that clear to you? Alright. So multipath. So basically as we go high in frequency, the lambda goes down. So, sorry, attenuation. Hold on. Let me just double check that. It increases with frequency. And so everything that I said, I got to double check that. Lambda is equal to C upon F. So C upon F square. Yeah, right. So this formula is not for the attenuation, it is for the received power. So that's why I was confused for a minute, because with F being on the bottom, as the frequency goes up, the received power decreases. So the attenuation goes up. Okay? Alright, now let's look at the multipath. So if you are going to receive, this is a transmitter, this is a receiver, and you will get many signals. Every building will be transmitting you some reflection of the signal. Right? And they will all have different phases. So what you get is, you might send this, just one pulse in time domain. Now you have to remember where I am talking about. This is in time domain. I just send you one square pulse. You will get 4 different square pulses. Actually, you might get n different pulses depending upon the number of the reflectors. So this came directly. This came from one reflection. This came from second reflection somewhere. This came from third reflection somewhere, and on and on. Okay. So every little point will be reflecting. So here is one way to think about this thing, that every building is a mirror, and you are sending a flashlight. You are just turning the flashlight. Some light goes to the mirror, and then mirror sends it that way, right? This is another building. This is another mirror. This is sending that way. There is another mirror. Everything is a mirror. If it was light, you will get lots of different rays. Here you will get lots of radio waves. Okay? So you send one and you get many. Yeah.
So the reflection is only happening with glasses?
Huh?
The reflection happens only with glasses?
Light is only, okay, so the thing, it depends upon the signal, right? Light reflects only with the glass. Radio waves can reflect with these things.
Everything.
Yeah, with everything. This table, that table, me, everybody is reflecting. Okay? Yeah.
And the frequency from one source, it can be divided into multiple sources.
So, did you say frequency?
Yeah.
Okay, so the thing is, I haven't talked about frequency yet. I'm just talking in the time domain. If you just send this pulse, which is just a very small impulse actually, right? In frequency domain, this will look very different. In frequency domain, it might be very wide in many frequencies. So I'm not going to take you there right now until I get there. So we'll talk about the frequency domain later. But in time domain, if you just send one pulse, you will get many pulses. So all the signals, whether it is radio wave or light or whatever, the same thing applies to fiber. You send them people inside. They are like a tunnel. If you send things or people who are very tall and very thin, beautiful people, what comes out is people who are very short and very thick. Okay? And so as the tunnel becomes larger and larger, they become smaller and smaller, of course, and they become thicker and thicker. So we all know about so basically if you send something, power, you send this, you send, let's say, a blue pulse and a red pulse in time domain. The blue pulse will come out as a very wide blue pulse. Actually, don't think about the color, it's just pulse number 1. pulse number 2 will also become wider, and they will start colliding in each other. I mean, if people become too fat, they will not fit in the tunnel. Right? And so you will lose lot of energy for nothing. Okay? So the decrease in the amplitude as you go down is called attenuation. The increase in the width as you go down is called dispersion. Okay, both things happen. Attenuation, we saw the formula. Dispersion is this width thing which we haven't really gave you the formula for yet. But I showed you dispersion, that I sent one pulse this thin and it came out like this thick. You see? So this is all one pulse I sent, and now it is kind of occupying this whole time. Now if I was going to send 2 pulses in the beginning here, they will be just getting into each other. Right? Because they are both wider in time. This width in time is called dispersion. Yeah.
Could you go to the next slide, please? Why at the very bottom, on the bottom right, the power versus time, why is it consistent power over the width of that? Shouldn't it be attenuating, or is it,
why power is less?
Yeah, why is the power consistent throughout the entire?
Oh, no. The thing is, this is simplification. This is simply, I don't want to go into, if I were to draw exact graph, I don't know what it will look like. It will be probably more complicated than this. I'm just trying to show that it is less, the height is less, means the power level is, less. And we already know that every d squared will come down, right? It will come down as a function of d squared. So it is less. And then we know the width will be high. Now I just showed you square pulses, doesn't mean that we will get square pulses. Actually, that's another thing, that actually they may not be even be square pulses, they would be multiple pulses like this, spread over all over. So, in fact, like this cartoon continues later on. If when I teach optical networking, which I do sometimes, then we use the same cartoon, and then there's some other phenomena. You send 2 and 3 people come out, if the tunnel is long enough. Alright? So there are all kinds of phenomena which are much easier to understand with the cartoon than with all the formulas that I give you. Alright. So multipath propagation is basically you send 2 pulses and you get lots of pulses. Okay? This one has 4 resulted in 4 pulses. Now this is not a square wave, right? Like you asked the question, right, Steve? So this one is not a square wave either, but now they're running into each other. Yeah.
If, let's say the last multipath pulse interferes with the first multipath pulse of the second signal, then will that interference cause a lot of loss of data?
Yeah, right. So that's what basically it is. So what happens is, if you know that in your medium this pulse can go this much distance, then you will keep the second pulse that much away. And that means you cannot send that many bits per second. This is second. You cannot send that many. If we call this a symbol, then we cannot send that many symbols per second, or bits per second. So you are limited, because multipath limits the number of bits per second you can send. And so this is called delay spread. Delay spread is the time between the first and the last version of the signal. And actually we don't take absolute last version, which may come million days later. We take up to certain power. Let's say I send 1 watt, or I send 1 dB, and if I get something up to 1/10 dB, that's all I care about, and anything less than that I forget. Yeah.
So is that one of the advantages of directional signals, that there's less
reflection? Well, that would be one possibility. Yeah, and the thing is, so there is a positive and negative for everything. So now you brought up this question, which I was not going to get into, but you see, if I just speak directional, then if suppose I happen to pick the wrong direction, then they cannot get it, right? So that is called deafness. And so there are all kinds of phenomena. Alright, delay spread. So delay spread is the word I wanted to introduce here. Delay spread means the signal becomes wider, and that is between the first and the last version of the signal. Fading is the fluctuation in the amplitude. Now the amplitude is not constant, right? And the delay fluctuation in the delay amplitude or phase or delay. That is called fading. And multipath may add constructively or destructively, so that is called fast fading. Basically, depending upon the phases, the signals may add, the signals may cancel each other out. So this is a little bit complicated, and I will show you a little bit of it. You don't really need to do all that math, because this thing is, if you pick up a book on wireless communication, and I have dozens of them, they are full of math. Okay? And that's a very important field, but we in this course are going to concentrate on the higher layers, and we just need to be able to talk to these people. So when they say there is a phase, there is a delay spread, you need to know that, because otherwise you can't write a paper on wireless. Okay? And so using a two-ray model. Now, it turns out that so far we have been talking about d square everywhere. So we have been saying that the power goes down by a function of d as a square of this distance. Actually, it goes down as a power of d. Most likely, it is different actually in different places. If you go and measure it might be 2, it might be 3 over there, might be 4 over there, might be 5 over there. So depending upon the location or the media or actually everything else, it could be any power of d. Most likely, most common value is 4. Okay? So that is called d raised to minus 4 power law. And if you just do a two-ray model, so people again, in wireless communication, people have shown that if you had a very simple thing, a transmitter here and a receiver there, then if they got two signals, one directly and one through reflection, if you add up, these two, you will get, this is a two-ray model, you will get formula which is received is transmitted times GP times GR times HT times HR, height of the transmitter times the height of the receiver divided by d square whole squared. So d raised to 4. And now you notice another term here, height. And so the higher you are, the more you receive, the higher you are, more you transmit. Because there is no transmission downward, everything that goes down is lost. Right? So that's why they put all these antennas on the top of the mountain, on the top of the big buildings, on the top of the long hotels, high hotel buildings. Yeah.
Is it because the lambda is somehow, like dependent on the height of the antenna?
Right. So no, hold on. The question is the lambda in here? Yes, lambda is in here somewhere, and that probably is gotten into GPGR. And so your question is, if I have a different lambda, would the height? Okay, so this formula applies to our lambdas here. Now let's see. Now the lambda is coming up in this next picture here, and that is that this formula is valid for distances larger than this value. So it is not valid formula if the transmitter and receiver are very close. Okay? If they are far away, and how far away? Farther than this, 4 HT 4 par upon lambda. Before that, actually, the previous formula was applying, which we had before, where we had clearly the lambda, but after a certain distance, this formula applies. I don't know whether to answer your question, but basically, so this is how it is related to lambda, is that for shorter distances, the original formula applied. For longer distances, this one applies, and the distance break is dependent upon the lambda.
So it's not an approximation, yes?
So longer the lambda, the longer the height, higher the height you need for that D break. Note that the received power becomes independent of the frequency. So it becomes independent of lambda after that distance. Measured results show that n is from anywhere from 1.5 to 5.5, typically 4. Okay? So, it turns out that sometimes if you move the receiver slightly, few centimeters, the signal may be very different than if it was few centimeters on the other side. That is called small scale fading. So the signal can vary basically, and by moving a little bit, you may get more power than less power and all that. So that is called small scale fading, and sometimes the small scale can add up to become bigger scale, or a small scale can cancel out totally, depending upon the phases again, right? If they're out of phase, they cancel out. If they're in phase, they add up. All right, so shadowing. Yeah, go ahead.
Sorry, 2 slides back, what was N?
Where? In this one?
The one previous, the very bottom.
Oh, this is the power of n. Okay, good question. So this formula is written here. If you were to write it, you will say, if you bring d to the top, it will be d raised to minus 4. Right? If you put there n, that would be the n, d raised to minus n. And n can be, for short distance it was 2, for longer distance it is 4. So the n is the power of d. So this is called d raised to minus 4 power law, is that this is most common value of power for d. So actually, so basically what it is saying is that the signal strength goes down as the 4th power of d. So if you go twice the distance from a cellular tower, you get 1/16th. So twice the distance, 2 raised to minus 4, yeah, 16th, 1/16th power signal. Now shadowing has to do with, if you have something in between, somewhere on the way, then it will cast a shadow. So if you are, let's say, just thinking about the light, you're flashing a light from here, and you're receiving it here. If something on the way, you will cast a shadow. You know, the light goes around, and then, you see a shadow of the building. Same thing, in the radio waves, you will see a shadow. And so what will happen is the received power as you move would be like this, shadow. Okay? Shadowing. So if you were to plot the power as a function of log, so here power is in dB, so this is already log, and the distance is in log d, you would get a straight line. Basically, if it was a 4th power law, this straight line will have a slope of 4. Maybe minus 4 or 1/4, something like that, right? So this will be a straight line, but it is actually not a straight power of 4. It is like this. The dotted line that you see, thin dotted line, that is the one we are talking about. That is how the power will look like if we were to measure the power. Thin dotted line. So first thing you can do is you can ignore the small scale fading, and you get this thick dotted line fading. And then if you ignore the fading, then you get a very thick straight line. Yeah.
Isn't it K over here?
Huh?
K?
What is K? K dB. Basically, PR upon PT is the ratio, right? PR upon PT. And so this is the attenuation. And so, K is basically the attenuation in dB. So by putting the word dB, we are making sure that you understand this is a log scale, not a linear scale. And K is just PR upon PT. And it starts from value K and goes down to value 0. So this is, let's see, it clearly says here, this is shadowing and path loss. This is the little thin dotted line is multipath shadowing and path loss. And this is the path loss alone. Path loss, then we add the shadowing, and then we add multipath. Okay. Then another term we use is Fresnel zones. So if this is the transmitter, base station, BS, if base station is the transmitter and MS, mobile station, receiver, if you were to plot an ellipse with those two as the focal point, you know how to draw an ellipse? Some of you must have drawn in high school using a string. You can put two pins and take a string and then put your pencil around and you can get an ellipse, right? So that's what you have to do. So if you draw that ellipse, all points on the ellipsoid have the same VS, MS run length. Run length means this plus that is fixed, constant, right? Because you took the string and then you moved around. So this line, this angle line and that angle line, they add up to the same value on every point, right? And so these are called Fresnel ellipsoid for which the run length is line of sight plus I lambda by 2. I is equal to, you put 0, you get line of sight. I equal to 1, you get line of sight plus lambda by 2. So if you put a string such that this thing is length of line of sight, which is already there, plus this is lambda by 2, you get the first ellipsoid. Then you can draw another one with 2 lambda by 2, 3 lambda by 2, third one, 4th lambda by 2, 5th lambda by 2. So you'll get lots of ellipsoid like that. All Fresnel ellipsoid result in a phase shift of I upon pi. Alright, it should be really the signal pi, not pi, symbol pi. So I upon pi, and this would be I divided by, not backslash. Radius of the ith ellipsoid at distance dt from the transmitter and dr from the receiver is I times lambda, this is I, times lambda times dt upon dt plus dr. So anyway, so the free space d square law is followed up to the distance at which the first Fresnel ellipsoid touches the ground. Now if these were high in the sky, then this is a ground here, and this is the first Fresnel zone. Wherever it touches the ground, up that is the distance up to which the d square law is followed, and after that it doesn't, right? We also saw that d break. So that's how we got this formula for d break, using these things. Basically you have the antennas and there are Fresnel zones around it, and basically depending upon where you are in which Fresnel zone, the signal properties are different. So we know a lot about how the signal propagates, and we are going to talk about now few other things, details, physical layer, and we will be done with the physical layer I think in this module, and then we will be talking more about the higher layers. But few other things that the electrical wireless communication people talk about are the diversity or multi-antenna systems. So previously we used to have one antenna, but now most of the things have more than one antenna. If you buy a router today, this will come with 3 or 4 or 5 antennas, right? And so we'll talk about why those things are used. And so receiver diversity, transmitter diversity, beam forming, and MIMO. And I'm going to talk about one by one. Receiver diversity means that the receiver can have many antennas, and then when it receives the same signal from this antenna, this antenna, this antenna, that antenna, it could multiply by A1, A2, A3, AM and then add them up. And so now, depending upon what value you choose for A1 through AM, you will get some received signal. So this is called receiver diversity, because the receiver is putting many antennas, and and then trying to get signals as much as it can. Now, how it can combine? It can do selection combining. That it could just measure the signal to noise ratio on each of these antennas, and then let's take the one which has the highest signal to noise ratio, which means the lowest noise, highest signal. Right? So we will just select one antenna, and then we don't worry about the other antennas. And then the next minute we again measure it, or next second, or next microsecond. We again measure it, and then we take the antenna with the best SNR. We could do threshold combining, in which case select the first antenna with SNR above a threshold. So if this one has high noise, we go to the next one. If it has good enough noise, we just stop right there. Maximal ratio combining. So the phase is adjusted so that all signals have the same phase. So we could put some value for A1, A2, A3. By the way, A1, A2, A3 do not have to be real numbers. They could be imaginary numbers or complex numbers. Okay? So generally in these fields, we talk about complex numbers because A plus IJ, because you see the horizontal and the vertical component, and then, so if you want to put 45-degree phase, you will have same A and B, A plus IB. That will become 45-degree. Right? So the imaginary part is vertical, the real part is horizontal, and so the whole thing is a complex number. Yeah.
Why should we use threshold combining?
Why should we use threshold combining? I want to produce a very simple algorithm. I don't want to do too much. So there is no reason. Basically, it's the designer's decision that this is good enough, and I don't want to do any complex multiplication, division, and this and that. Okay.
Selecting the high signal makes more sense,
I know. I'm not going to argue about one against the other. People have suggested, and these are possibilities. And it's not necessary that you say one or the other. When you really design it, you will know much more than this. Right? So some way, all I'm saying is I'm just giving you diverse opinion about diversity so that you know that it is basically many possibilities of how you combine these things. Same thing the transmitter could do. Transmitter could have many antennas, and then it could put different signals on each of them. It could multiply by some complex numbers and then transmit. And so ample space, power, and processing capacity of the transmitter. And this might be done particularly if the transmitter has a lot of money, which generally is the case. So cell phone company has a lot more money than we do. So cell phone company might put 10 antennas, and while we have little money, so we can only buy with one antenna or two antenna a cell phone. So in that case, the transmitter will have diversity, and we all benefit. And if the channel is known, we can find out the phase of each component and weigh in before the transmission. So this is what we haven't done is basically the channel is estimated continuously. So we continuously see what is sent, what is received, and we figure out what is the channel model, and depending upon that we can adjust these values. If the channel is not known, then we use something called another magic, which is called space-time block codes, and I'm going to explain that too. If the channel is not known, then we use space-time block codes, which we'll talk about later. But before that, beam forming. Beam forming is basically making the antenna directional. So the antenna is directional, and that is like, you're putting your ear. If you want to receiver directional, then you put your ears towards the source somehow. And if you want to have transmitter directional, then you put your transmission that way. And so the interesting thing is that you can change the direction continuously. So I could transmit to this direction and then change in a microsecond to that direction, to that house, and then transmit and come back to this. So there are antennas which can change the direction continuously. Now, of course, they can move. If you are going to go to this satellite, that satellite, then they will come at the beginning of the year and move your antenna for the rest of the year. It is pointing to another satellite, but that is not what we are talking about here. Here we are talking about something which doesn't move, but the signal changes. Okay. So by phase shifting various received signals and then summing, we can focus on a very narrow directional beam. Our digital signal processing is used for signal processing and self-aligning. So digital signal processing, I use the word DSP. So that's a whole field of DSP, digital signal processing, where you take different matrices and then you multiply them and you somehow get the result. We are not going to go there, but you have to just know that there are such things. So they can do beam forming. And beam forming, all it means is making the signal directional towards the receiver. And that takes us to the next concept called MIMO, multiple input, multiple output. So if the transmitter has multiple outputs and the receivers has multiple input, so each of these receivers will receive many signals from many different outputs and many different reflections of those outputs. Right? And then you can do some DSP around here and somehow get lot more signal. In fact, if you did the things right, then if this guy has 2 and you have 3, you should be able to get 6 times more signal than if you had just 1 antenna each. Here's the thing, if the transmitter had 1 antenna and the receiver had 1 antenna, they can get some signal with all these reflections and everything else. Now they say, no, look, transmitter, you buy 1 more. So transmitter has 2 antennas, so now at least you should be able to do twice as much work. Right? Now the receiver says, I am going to get 1 more, so they have 2 more, so 4. So they should get 4 times. But in practice, you don't get that. You generally get somewhere in between the minimum and the maximum. So the minimum is the minimum of these 2, which is 2 by 3. The minimum is 2. And the maximum could be 6. Okay? But, so here is the thing. For WiMAX, 82.16e, for WiMAX at 2.5 gigahertz, using 10 megahertz TDD, and all these symbols will, if they don't make sense, it doesn't matter really right now, because when you present any numbers, it's good to tell what the numbers apply to. So we are just telling down to upload ratio of 2 to 1. But basically, you will understand this when we come to WiMAX. The transmitter to receiver, if it is 1 by 1, the signal, you could get 1.2 bits per hertz. With 1 by 2, you could get 1.8. With 2 by 2, you could get 2.8, 2 by 4, 4.4, and 4 by 2, 3.7, 4 by 4, 5.1. These are measured numbers in some lab or in some environment. They could be different in some other environment. But this is just a simple example saying that with 4 by 4, you don't get 16 times, you only get 5 times. Actually, if you divide by 1.2, you only get 4 times. Okay? And so with 1.1, you can get 1.2 bits per hertz. With 4 by 4, with 4 by 2, you get 3.7. So this is a complex system. But MIMO helps. It may not be straight linear common linear factor of whatever you put in, but you get better than 1. And that's why everything is MIMO today. Okay? Even your phone is MIMO. Everything is MIMO. Now, we move to multiple access method. Now, we already talked about multiple access method, but I just want to tell you how the things have progressed in time, history. Basically, we talked about multiple access method, time division multiple access, TDMA. By the way, always be clear what you mean, multiplexing or multiple access. TDM, time division multiplexing. TDMA is time division multiple access. A lot of people confuse. I have seen read papers and reviewed papers where people don't know the difference and they just use one for the other. Okay? So multiple access is when multiple people are trying to share the medium by design. And so TDMA, so basically 1G, the first generation of cell phones had FDMA, frequency division multiple access. What that meant was the cell phone number 1 will use this frequency, cell phone number 2 will use a different frequency, third frequency, fourth frequency, and so on and so forth. Every phone was assigned a frequency. Basically, the first thing you did was you told the tower, look, I want to talk, and they will say, okay, now talk on this frequency. Okay, so that was FDMA. 2G was TDMA. Okay, GSM is TDMA, GSM, right? So basically, when you talk, they tell you what time you should talk. So they had slots. You're on slot number 5, you're on 6, you're on 7. So you selected your slot and you talked in that slot. Nobody else talked in that slot. TDMA. Huh? And the whole frequency, yeah. 3G is CDMA. So you talked at all the time on all the frequency, but you had a different code. Everybody used a different code, but you used all the time and all the frequencies. And 4G are actually 3 plus G, because 3.5, 3.9, 4, 5, everything else in the future and today, right now, as far as you know, is using OFDMA. OFDMA is orthogonal frequency division multiple access. And I'm going to explain what that is. So OFDMA, in OFDMA, everybody has both combination of everything that we have talked about. Is that you have a time, you have a frequency, and other things as well. Okay, so but you are given a slot and a frequency. Okay, but there is more. So let me talk about OFDM first before we go to OFDMA. OFDM is orthogonal frequency division multiplexing. And it will become clear as to what is multiple access and multiplexing on this slide. So basically, if you are given a very thick pipe to send something, you have two choices. To send one signal which takes the whole pipe, or send many signals, each taking little bit of the pipe. It turns out the second method is much better. Okay? What it means is that if you have a 1 megahertz channel, it is better to send 10 100 kilohertz, to divide it into 10 100 kilohertz channels like this, rather than have one big one. Okay? And so it is better to use tiny channels than to use thick channels. So basically, total number of bits that you will get by tiny channels is much higher than with the thick channels, and it will become clearer as we go more and more into some more theory. So basically, people decided that this is better, and therefore they started dividing the band. So frequency band could be divided into 256 or more sub-bands. Actually 256. You could do it with 4 bands to it. It's not that. So 4 bands are better than 1, 16 are better than 4, 256 is better than 16, and on, you know, 512, 1024, as many bands as you want to put. So it is good to have very small channels. And they have to be done orthogonally. Orthogonal means the peak of one is in the low point of the other. So this is one band and this is other band. You notice that the peak here for the black is at the bottom of the red, and the peak of the red is at the bottom of the black and the blue, and the peak of the blue is at the bottom of, you know, their neighbors. Right? And this is basically the power of that channel. So the highest power happens at that frequency, and then the lower power goes around it. And so this is how you divide it. Now each of these is a band, right? It is a small band. On each of these bands you can send a signal with BPSK, QPSK, and, you know, QAM, and, you know, 256 QAM. Whatever you do, you can do it on each band. And in fact, you can do a different QAM on each band. So on the red, you could do 256, On the black, you could do 4. On the blue, you could do 124, and so on. All right? And so this is what, once they discovered it, this has become a norm everywhere. Even on the wire, they use it. So when you get a DSL at your home, previously the DSL was running at very low speed. Now they're offering higher and higher. Sometimes they give you 3 megabits per second, then they give you 16 megabits, then 20 megabits, then 30 megabits. So there are several things they're playing with. One, they're playing with QAMs, but they're also playing with OFDMA. On the wire, they send many, many tiny channels. Okay? And the reason it is possible now and it was not possible in the past is because now we have FFT and IFFT. FFT is the fast Fourier transform and inverse fast Fourier transform. Right? Now we can do that very fast. Fast Fourier transform is fast, right? So there are chips that come, and DSP chips we call them, digital signal processing chips. So you can buy DSP chips. We can do in microseconds and nanoseconds all this calculation, and we can handle 1024 channels at the same time. 1024 is small for today. We are just going up and up in the numbers. Previously, we were not able to do 256 QAM. Then we talked about, we can do 1024, 2000, 4000, 8000. Similarly here, we were not able to do too many channels, 256, then 1024, and on and on. So the numbers keep going up and up. Okay? So this is called OFDM. So this is orthogonal frequency division multiplexing. And multiplexing means that many people going in the same direction. Okay, like duplexing. So this is going in this direction, this is going in this direction. In this case, multiplexing, we are going in the same direction at the same time. Right? Where multiple access means that somehow we share it. So this is more of how you come in and how you get out. And this one is how you move. So advantages of OFDM. OFDM is very easy to implement. The computational complexity, for those of you who understand this term, it is order of B log BT. B is the bandwidth and T is the delay spread. B is the bandwidth and T is the delay spread. If you have a channel which has a delay of T, a spread of T, and has a bandwidth of B, then this is compared to OB square T for equalization. So previously if you had a big channel, the problem with the big channel is that the power is everywhere different. So here if you had this much frequency if you have to plot from frequency from here to there, the power would be very different, and then you have to do equalizer so that they all look same. So it is much better than that. Graceful degradation if excess delay, so the things don't just kill each other. Robustness against frequency selective burst errors. So suddenly you get a noise in the middle of some place, it just doesn't kill you. Allows adaptive modulation and coding of subcarrier. So each subcarrier can be modulated differently. Adaptive means if there's more noise, you can put a lower QAM on this. If there's less noise, you can put higher QAM on this. Robust against narrow band interference. So if there is something that only affects a small part, this is narrow band interference. This is robust against that. Allows pilot subcarrier for channel estimation, and you don't have to use all the subcarriers. You can use some of them just for pilot, which means to measure the system. So every 4th, 5th, every 8th, every 16th band is used for measurement. It's called a pilot. Yeah, question.
The O stands for the second line.
Complexity?
Yeah, computational complexity, the O stands for
Order of. Okay, so I don't know where they teach this complexity stuff, but there is some course in computer science. So whenever you have an algorithm, okay, it has to be, we have to measure the complexity of the algorithm, and the complexity could be order n, where n is the number of people, and is something, whatever parameter n is. It could be n squared. So as the number n goes up, the complexity goes up. The computation time required for that, CPU time required for that, is power of order of n squared, n cube, and it could be exponential in n, in which case we say np complete. Right? So this is basically all saying is that if you double B, the work becomes double. It is order of B. and log BT. So, if you double T, it doesn't affect too much. Right? So, you calculate what is inside, and that will tell you how much your work will go up if you change B or T. Right? So, this is almost like a linear, so we would say this is a linear complexity because log is, almost like 1. Right? So, it's linear complexity.